Welcome to the lecture on acid-base definitions. We're going to be talking about Arrhenius, we're going to talk about Bronsted-Lowry, and we're going to talk about Lewis, acids and bases. There's three different ways to kind of think about acids and bases and talk about them, and so today we are going to be going over that. Also, when we talk about the Bronsted-Lowry relationship between acids and bases, what we are going to also do is see what the conjugate pairing is for those acids in their conjugate base and the bases in their conjugate acid. So let's go ahead and get started. All right, so first we want to talk about Arrhenius, which is what we kind of call the traditional acids and bases. And so if you look here, acids, when we put them into water, they're going to dissociate. And any acid will dissociate to create hydrogen ions. All right, so that means that anything that starts with an H is going to be an acid. So that's like H, S, for example, H2S it would be. I would put that in the water and it would make sulfur -2 and some hydrogen ions in the solution. Anytime you see that H leading in a molecule, that the H is out front, that means that it's an acid and it's going to dissociate to produce those H plus or H3O plus substances in the solution. Now, Arrhenius also looked at bases, and he said that bases produce OH minus in water. So if I had, let's say, LiOH, and I put that into the water, all right, it would produce OH minus ions, and those are bases. So the problem is that some bases don't have a hydroxide ion. So in a minute, we're going to talk about Bronsted and Lowry, who came along and kind of redefined bases for us. And this is why we have multiple ways to talk about acids and bases. Here we have hydrochloric acid and water. And when we put that in water, this hydrogen here is going to bind here and leave a Cl minus. And so this hydronium ion is created in the water, and that is our acidic hydrogen. Now, a base produces hydroxide in water. So here's ammonia, which actually does not have a hydroxide on it, right? But water does. If you look right here, this is a hydroxide. So if we remove this by sticking it on our ammonia, now we have the ammonium ion and a hydroxide. And so this does donate or produce hydroxide ions in water, and that is what makes it a base. All right, so when we get to the Bronsted-Lowry definition, we are going to see that an acid is a proton donor and a base is a proton acceptor. So this is a little bit more of a simple way to look at the relationship between acids and bases. Why do we say a proton? Well, really, if we look at this hydrogen that's over here, if it becomes an ion, which we know means that it loses an electron, what's left? Oh, just a proton, this little P plus in the middle. So when we become a positive ion, what we do is we lose that electron, and so we can call this a proton. So that means that an acid that releases H pluses is really releasing a proton into the solution. A base is taking that proton out of the solution. And so that's an important thing for you to realize, that that proton is really just a hydrogen atom that lost its electron. All right, so here we see this relationship between acids and their conjugate base. When I have an acid, I become a conjugate base by donating a proton. And if I'm a base, I become a conjugate acid by accepting a proton. And so what's the only difference between an acid and its conjugate base? It's a proton or a hydrogen ion, right? A base and its conjugate acid, the only difference again is that H plus or proton. All right, so what we say is, since there's this proton donor, where did the proton go? The proton went from here on to here. All right, so if we look at the pairs, a base is paired with its conjugate acid. What's the difference is we're going to add an H plus. Whereas an acid is paired with its conjugate base. The difference between this and this is an H plus. And you can see that here in the actual molecule. What's the difference between these? An H, right? And the difference in the NH3 versus the NH4, the only difference is that H plus. And so anytime that you're looking for conjugate pairs, you're just looking to see if there's a difference of hydrogen. All right, so here is a base and an acid. And the Bronsted means that ammonia is a base in water, and water itself is an acid because it's acting as an acid in that case because it's donating the hydrogen. Right, so that hydrogen is donated from the water, making a base. Here's our conjugate pairs again. We kind of talked about this a second ago. If we have HCO3 minus, what's the difference between that and CO3? A hydrogen. What's the difference between the charge? One charge. That means that they are a conjugate pair. Difference here, one hydrogen plus, right, H plus. All right, so try these reactions. HCl plus OH minus makes Cl minus plus H2O. You should be on the back side of your notes at this point. What is the acid and what is the base? All right, first let's look at our pairs. HCl, what compound is it only different by a hydrogen? Chlorine. How about OH? What is it paired with? Water. Now, which one donated the hydrogen? Well, if you look here, HCl gave away a hydrogen to become Cl minus. If you are a hydrogen donor, you are an acid. And we know that HCl is hydrochloric acid. OH minus is the straight up definition of a base, is something that has hydroxide in solution. It is hydroxide. And so that is acting as our base. So our acid and its conjugate base, our base and its conjugate acid. Try this again. All right, so hopefully first you kind of looked at it to see H2O, its pair must be H3O. And H2SO4's pair must be HSO4. Why? What's different between these? One of these things is not like the other. Well, it's a hydrogen ion. Here we have two H's, here we have one H. Here we have no charge, here we're on -1. That means the difference is a H plus. Now, this gave up a hydrogen to become this. If you give up a hydrogen, what are you called? An acid. So that means the other one must be a base. Now, water, you might think, well, water is neutral. In this case, it's acting as a base because it accepted that hydrogen. And remember, a base is a proton acceptor. And so water is actually amphoteric, which means that it could be either a acid or a base. All right, so right now on your paper, it says to watch the video about conjugate acids and bases, but I will have a link to that at the bottom of your notes here so that you can go straight to it after you watch my video. So don't worry about that until we get to the end. Let's talk about Lewis acids. All right, so if you remember Lewis, what was Lewis known for? Well, he was known for his Lewis structures, and those had the dots that were around the atoms to represent what? Yes. You remember this. What do they represent? They represent electrons. So Lewis is like the electron king. And so Lewis said, oh my goodness, all these definitions that they're talking about protons, but I believe that an acid and a base could be defined just by the exchange of electrons. All right, so a Lewis acid is a substance that accepts an electron pair. Now think about it. All of our other definitions, we were giving away positivity, right? We're giving away hydrogen ion. But now, let's say you start accepting an electron pair. It's kind of the same concept. A Lewis base then donated the electron pair. All right, so here I have acid, and that acid goes onto the base. So these electron pairs become this bond, and so it's donated the electron pairs to the acid. So originally on that Lewis base, these electron pairs were part of the Lewis base, but now they are a bond. And so that's where the donation came from. And so when we do a reaction, here we go, we have H plus and H2O. These become donated to a bond. Here we have our H plus again, and these become donated to make this bond right here. The reason why Lewis came up with this is really interesting because when we talk about biological mechanisms, we don't always have these traditional strong acids and strong bases, the hydrogens, the hydroxides, because it's in your body and those things are dangerous, and so our body doesn't keep them around. But hemoglobin can interact with O2 and CO because the iron ion that's in the hemoglobin, which is where the term heme comes from, because iron is a heme, that heme group, and that's a Lewis acid, which means that it is accepting the electron pair from the O2 and the CO in order to bind on to that oxygen, take it to the cell, and then bind to the carbon dioxide and take it to your lungs. Those are acting as Lewis bases because the O2 is donating those electron pairs and the CO is donating the electron pairs in order to bond to your hemoglobin and stay in your bloodstream. So thank you to the Lewis acid-base system for our entire mechanism of breathing. All right, so that is the end of this lecture on acid and base definitions. So go ahead and watch the video that we want you to watch over in videopediaworld.com. I will link that at the bottom of this, and I will see you in class. Have a good night.